Hello everyone, it's a pleasure meeting you all in my mathematics class. Today let me discuss some theorems connected with convergence and divergence which will help the students to solve problems connected with convergence and divergence, that is to find out to determine whether a given series is convergent or divergent using some tests. When the students apply the tests, they must be confident enough and they should have well understood the concept and the theory that they will be able to tackle any problem confidently. With that idea in my mind, I am starting my lessons on the theory part of it, that is discussing the theorems, various theorems. See, let me go with this theorem, that is convergence theorem. If an 1 to infinity is an increasing sequence which is not bounded, then the sequence is a divergent sequence. And if there is upper bound, then it is convergent and converges to the LUB, that is least upper bound of n belongs to n, that is supremum. So this is the theorem that we are going to discuss. If an is an increasing sequence which is not bounded above, it is not bounded above, I must put it here that. Then the sequence is a divergent sequence, and if there be an upper bound, if it is an upper bound, then it is convergent and converges to the least upper bound, or we call it as supremum. So this is the theorem that we are going to discuss. Okay. Now, let me take the sequence. See what is given here. Given is an increasing sequence. What is the meaning of this increasing sequence? That is A1, comma A2, comma dot, AN, it runs to infinity, is an increasing sequence if an plus 1 is greater than or equal to an for all n. So this is the definition or the understanding of what is an increasing sequence. So this is an increasing sequence, therefore every term is greater than or equal to the every term is greater than or equal to the immediate preceding term. See, an plus 1 greater than or equal to. So A2 greater than or equal to A1, A3 greater than or equal to A2, so like that it goes on. Now, if there it is not bounded above, that is, if there is no upper bound, then we have to prove that this is. So, first case 1. Case 1. There is no upper bound. See, there is no upper bound. There is no upper bound for this sequence. That means it is, the series is like this. It goes on, increases like this. It goes up. It goes up, and you see that it is steadily increasing. It is increasing actually. It is increasing. And let for some positive number m, and for some capital N belonging to set of all natural numbers, a n be greater than n. See, what does this mean? See, this is an increasing sequence. So for some value here, some n, somewhere I choose here. See, let us suppose it is for some large n. I go to, that is, I go to some large value of this n, small n, because n, I take the large value of n, say capital N, and let us suppose that because it is an increasing one, the value has to be positive. Therefore, I take a n to be greater than m. A n is greater than m. That is nothing there with this thing. And m is a positive number. Now, since this n, so it is therefore for all n, see, therefore for all n which is greater than n, a n will be greater than this m. This is quite logical because they are all positive, they are all increasing sequence. That for this n, arbitrary n, we have taken it to be greater than some m. Therefore, for any n after that, for any n greater than n, a n is greater than m. That means it is steadily increasing. The value of a n is greater. Therefore, this simply implies that as n tends to infinity, a n tends to plus infinity. A n tends to plus infinity, and hence this will be a divergent sequence. So this simply implies that this a n is a divergent sequence. This is very, very simple, and that this is sequence is a. So I'll repeat this. A n plus 1 greater than or equal to a n for all a n means the sequence must be a increasing sequence. Okay, monotonically increasing. I should say that it is monotonically increasing. Here, see, monotonically increasing. Monotonically increasing sequence, and therefore it is greater than or equal to, that's all. Okay, now let me choose any m which is a positive quantity, because all are increasing, they are all positive quantity, for which I choose some n which is from the set of all natural numbers, that a n is greater than m. But after this n, if we take any term, it will definitely be greater than m. Therefore, for any n greater than n, a n will always be greater than m. Therefore, when n tends to infinity, this a n will be tending to infinity, which ultimately explains the fact that the sequence have to be a divergent one. So this is the small discussion on this. Now, case 2 let us take. What will happen to case 2 if there is a bound? So, if there is a bound, let there be a bound for the sequence. Let there be a bound for the sequence. Now let us see what happens to this so let us now discuss what will happen to the sequence if there be a bound. So the curve goes like this. See, it is like this. It increases and it goes like this. Now this is a sequence in which we suppose that there is a bound. In the first case, we said that there is no bound. Therefore, the series will tend to an will be tending to infinity plus infinity. This an tends to, that is n tends to infinity means this an will tend to, if n tending to infinity, an will tend to plus infinity, and hence this will be a divergent sequence. But now in this particular case, I am telling that there is a bound. So let me take that bound. So let the least upper bound of, see, least upper bound of all an, where n belongs to n be equal to n alpha. So this least upper bound is nothing but your supremum. So I am taking the supremum, that is a supremum, and know that it is a unique number. It is a unique number. Supremum or least upper bound is unique, and greatest lower bound is also a unique number. Now this is a unique number and we are taking that to be alpha. That means all values of this sequence will be less than alpha. So what is the meaning of this? This alpha supreme least upper bound means all the terms that you are getting will be less than alpha. That is the meaning of this. Now let for some epsilon, that means here somewhere here, for which it will be, say it will be here, and you see that all numbers will be less than this. So let us suppose that let for some epsilon greater than 0, let epsilon greater than 0, see, we will consider alpha minus epsilon such that what? So this cannot happen. Let us assume that for some epsilon, which is a very small quantity, and it so happens that for this alpha minus epsilon, there exists an n belonging to set of all natural numbers such that this an will be less than, will be, or this an will be your an, sorry, this one. See here you see that it will, all numbers must be less than this. So for this an will be greater than alpha minus epsilon. So let us suppose that there is one. You must know that this an for all values of n, it must be less than alpha, because alpha happens to be the supremum. But let us suppose that there is a smallest value epsilon in such a way that for a particular n greater than, that is after this capital N belonging to a set of all natural numbers, an is greater than alpha minus epsilon. Normally it has to be all less than, but let us suppose that there is alpha minus epsilon existing, that an is greater than alpha minus epsilon. That is, therefore, see this an, but therefore for this is after all an arbitrary one. Therefore, for n greater than n, an is greater than alpha minus epsilon. This is alpha minus epsilon. Now you see that I'll write it here to make you things very clear. So therefore, see, so that is an is less than alpha minus epsilon, that is alpha minus epsilon is greater than an, greater than an. This an alpha minus, there exists one that is for alpha minus epsilon, all values must be greater than, less than this alpha, but let us suppose that there is one an for which this is greater, therefore alpha minus epsilon will be less than, see, will be alpha minus epsilon will be less than epsilon. See, can you catch this? See, there is some, for this n, all values must be less than the upper bound, but we are supposing that for some epsilon which is before this alpha, alpha minus epsilon, there is an an which is greater than alpha minus epsilon. Therefore, this in turn will imply that an is greater, see, an is greater than alpha minus epsilon. Therefore, this alpha minus epsilon must be less than an, because I am just reversing the, that is, we are writing it in the other way. That is, an is greater than alpha minus epsilon means alpha minus epsilon is less than an. But we know that this an is definitely less than alpha, because the alpha happens to be the upper bound. So, but see, but an is less than alpha, therefore alpha minus epsilon is less than an, which is less than alpha. See, you must understand why this is being used. I say that this, since we know that an, whatever, since alpha is, say LUB, alpha is least upper bound, alpha is least upper bound, therefore an is less than alpha, therefore alpha minus an epsilon less than an, which is less than alpha. But this in turn, this implies that alpha minus epsilon is less than an, is less than alpha, and it has to be still lesser even if you add a small quantity plus epsilon. So it is not going to change, because after all you are adding a positive quantity. Therefore alpha minus epsilon less than an, which is less than alpha plus epsilon. So this, it implies that an is greater than alpha minus epsilon, an is less than alpha plus epsilon. So you see that this can happen. Now this, from this I can conclude that, so this implies, see, subtract alpha throughout, that means minus epsilon less than an minus alpha, an minus alpha, which is less than plus epsilon. So you see that here you get an minus alpha is, this an minus alpha is less than epsilon. So from this I get alpha minus epsilon is less than an, less than alpha plus epsilon. But you subtract alpha throughout, so you will get minus epsilon less than, that means this implies an minus alpha is less than minus epsilon, an minus alpha is greater than, it is greater than minus epsilon and less than epsilon. So you see that this inequality tells us that an minus alpha is greater than minus epsilon, but it is less than plus epsilon. So this, what does this imply? This implies that an minus alpha is less than epsilon. An minus alpha is less than epsilon. But so this is nothing but the actually gives the definition for a sequence to be convergent. So this simply implies, so by convergence principle, by convergence principle, this implies, one implies that limit of n tending to infinity of an will be equal to your alpha. This implies that an is a convergent sequence and converges to a least upper bound alpha. So this is all about this. But so I will repeat this. You must know that alpha is the least upper bound. So L minus alpha minus epsilon cannot be there because I told you that there can be only one upper bound, least upper bound. But let us suppose that L minus epsilon is there in such a way that for some capital N, an is normally alpha, it will be less than the least upper bound. All numbers will be less than the least upper bound. But let us suppose that an is greater than alpha minus epsilon for some epsilon greater than 0. But this will in turn mean alpha minus epsilon is less than an, that is alpha minus epsilon less than an, but an is less than alpha because alpha is your least upper bound. Therefore, alpha minus epsilon less than an, less than alpha epsilon. You subtract this alpha, so and then you get out of this. Then from this I can write an minus alpha is a modulus is less than epsilon, which is nothing but that gives the definition for a sequence to be convergent. Therefore, limit n tending to infinity of an will be equal to alpha, which converges to the least upper bound. And therefore, when a sequence is increasing and has got a bound, then you must know that it is a convergent. Otherwise, it's a divergent series. Okay. Now, with this idea in mind, let me do the other one. That is, if it is for a decreasing sequence. Let an 1 to infinity be a decreasing monotonic decreasing sequence, that with no bound, that is, it is unbounded. It is unbounded. Now, a1, a2 dot dot dot, an plus 1 dot 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 infinity is monotone decreasing sequence. This implies that an will be an plus 1 is less than or equal to an for all n. That means a2 is greater than, a1 is greater than or equal to a2. And here you see that this in turn means that an is greater than or equal to an plus 1. That means every term is equal to or more than the succeeding term. So such a term will be called. Now it is not bounded. It is not bounded. See, since it is not, that means what? It is like this. It is coming like this. So it will be going to minus infinity actually. So we have to prove that. So let m be such that, let m be a number such that for an n belonging to the set of all natural numbers, this an is less than a positive quantity m. So it is decreasing. Therefore, I am taking it as an less than m. Therefore, for n greater than n, this an will be less than m. So you see that since it is a decreasing sequence, for I will choose that it becomes, the an becomes a small quantity. M is a positive quantity. Try to understand that m is a positive quantity. But you must know that it is slowly decreasing and decreasing and decreasing. It is going down. Therefore, an is less than m. It is a particular quantity. But for an n which is greater than capital N, let us suppose that for say n greater than this n, greater than this n, an is less than m. This implies that as n tends to, see, this becomes smaller and smaller, it is going down like this. So you see that as n tends to infinity, an is tending to minus infinity. Therefore, an 1 to infinity monotonic decreasing sequence, no, not bounded, is a divergent sequence. So this is a divergent sequence. Now let us discuss the case. This is your case 1, not bounded. Not bounded. This is your case 1. Case 1. So when it is not bounded, this is a divergent. So this is divergent. It's a divergent one. Now let us suppose that there is a bound. Let us suppose that there is a bound. See, next case 2 is, see, an is greater than or equal to an plus 1 for all n. See, an monotonic decreasing sequence with bound. See, case 2, there is a bound. There is a bound. That means there is a lower bound. In the case of this monotonic increasing sequence, upper bound, but here it is a lower bound. So there is a lower bound. So let us suppose that see, the greatest lower bound of n belonging to n be equal to your beta. Therefore, we will take, see, for epsilon greater than 0, for n belonging to n, let beta consider, see, I will write it here, consider beta plus epsilon. I consider this beta plus epsilon such that, so that beta plus n and this and for n belonging to set of all natural numbers, an will be less than beta plus epsilon. Now this is correct. So I will explain this. So this is our greatest lower bound is beta. So all the terms here must be what? More than this beta. But let us consider there is one beta plus epsilon which is more than beta, which is cannot happen because we are taking this beta to be the greatest lower bound. But we will consider this beta plus epsilon for epsilon greater than 0 such that this an normally it has to be less than, but let us suppose that this is an must be greater than beta, but we are taking this an is less than beta plus epsilon. We will consider that is for therefore this one therefore for n greater than n, this an will be less than beta plus epsilon. This you must understand because I am considering beta, which is the greatest lower bound, that cannot be more than that, but for we will consider this beta plus epsilon to be more than beta in such a way that you have got all must be greater than, these all ans must be greater than beta, but we will suppose that an is less than beta plus epsilon for a small value. It is like this. It is going like this. See, it is coming down like this. See, it is coming down. It is coming down like this. For this beta, it may be here, and for some value of very infinitely small is epsilon, let us suppose that an is less than beta plus epsilon. Okay. Now, an is less than beta a plus epsilon. Now you see that an is less than beta plus epsilon, but we know that an is always greater than beta, or beta is less than an, because beta a happens to be our greatest lower bound. Therefore, but beta is less than an, therefore beta less than am less than beta plus epsilon. So what do you have here? Here you have got this inequality relation. What is the inequality relation that you have got here now? So we have got this beta is less than an, which is less than beta plus epsilon. I told you how we are getting this, because we have supposed that the beta plus epsilon exists, that an is less than beta plus epsilon. But you must know that all ans are greater than beta. That is why you see that beta is less than an. Therefore, beta is less than an and is less than beta plus epsilon. Therefore, I get this rate. When beta is less than an, we can very well write beta minus, because after all this is a positive quantity, beta minus epsilon is less than an, which is less than beta plus a. There is no harm in writing, because beta itself is less than an. Therefore, beta minus epsilon is still, it will be the inequality is maintained. Therefore, beta minus epsilon is less than an. Now, you see that subtract this beta throughout. So, this simply implies minus epsilon less than an minus beta, which is less than epsilon. See, throughout subtract this beta you subtract, therefore. So, this means that an minus beta is greater than minus epsilon. An minus beta is less than epsilon. This implies that an minus beta is less than epsilon. This gives, now we have come down the definition of the convergence of a sequence. So this clearly means that by convergence principle, an minus beta less than epsilon implies that limit of n tending to infinity of an is equal to beta, that is an monotonic decreasing sequence converges to least greatest lower bound beta as n tends to infinity. Therefore, the sequence an is a convergent sequence. So this is all about. So here you must know that in the previous case it is alpha minus epsilon, but here it is beta plus epsilon. That's all. So with that idea, I have explained fully. Go through that. If you have any doubts in that, you write to my email address, and it will be attended. Thank you.